kind of back pointer stuff, and yeah, children that have several parents, so to say. So you have things that couldn't happen in a real tree, and you have to use some escape codes for the exceptions, for stuff that couldn't happen in a tree. You need a special symbol for that. You basically just pretend it's a tree and code exceptions when it's not. That's the most efficient way to store the structure of this operator graph, of the data flow in the intro. But it's not the most efficient way to store the parameters to these operations. Because don't understand the question.
How do you know this way is most efficient?
Because it's very implicit. You this kind of stuff you need to code. Yeah, you code a minimal amount of information. You need the minimal amount of information. Yeah, well, it's a minimal amount of information you need to code. You need those operator type IDs anyway. And any other way to code it needs some additional information as well. I mean, this is not mathematical.
Well, that's a proof. That's a proven fact, and that has been proven 30 years ago. I mean, that's just basic knowledge. You can prove that the entropy is exactly that, the post-traversal ordering.
But this is DH done. This is DH key.
Yeah.
So this exception, escape code. Okay.
Yeah, sure. This is not.
I don't know if it's most efficient.
I don't mean it in a way, as in you couldn't squeeze a few percent out of that, but you could probably do some fancy escape coding stuff, but it's not really relevant to what I'm trying to say here, so I just skip that. And yeah, of course it's a risky statement, and you could probably prove me wrong, but I don't think it's really relevant at this point. So I'll just skip this discussion and go on with the operator parameters. Because the problem there is that those parameters are different beasts from the type IDs. They have a different structure. The straightforward way is to store that together with the op type. So you just store this op type, and then the parameters for this op, and the next op in this post-order traversal. When you do that on the data set we used in the Krieger beta version, you get about 30 kilobytes packed again with a simple encoding I mentioned. But a fact is that, again, operators of the same type, like most cubes, have a very similar setup because certain parameters like tessellation you usually don't change. You want those in any way because some cubes need a special tessellation, but a lot of cubes will simply be 1 by 1 by 1 faces and that kind of stuff. So operators of the same type tend to have similar data. And this tells us that it's a good idea, probably, to try to group them so we can exploit the differences between them better. And so what we try is we store all operators of the same type together. But to do that, we obviously need to store the tree and the operator parameters differently in a separate way because, by now, the operator data doesn't happen in the same way, in the same order as it does in the tree. When you do that, you get about 28 kilobytes, or about a 7% gain in compression ratio. And the changes to the loading code are really quite minimal, because it's undoing this reordering is basically just changing. Just building a list of pointers first where every data is, but and you have to sort it first, but it's not a big problem. It's not a lot of code, maybe 50 bytes additional. So this is no huge gain in compression you get there, about 2,000 bytes, but it's at a cost of about 50 bytes of code. So it's an easy saving. It's really a no-brainer to implement, and this kind of stuff, if you do several things like this, it can give you a nice gain in compression without having to do a lot of work. And the second example I was going to mention is x86 Intel architecture code. Basically your intro is probably at least half of it is code. The source code is usually in a highly structured form. You use structured programming languages which have for loops and while loops and the like. So you try to make it's a relatively high-level representation with a lot of explicit information. And if you look at the compiled code, it looks quite unstructured. It's basically a sequence of just straight-line code with some if and goto instructions. That's what it maps to on an assembly level. And when you view it in a hex editor, you get a sequence of very random-looking bytes. So there are two possible explanations for this. The first one is that this process of compiling source code into executable code completely destroys the structure that was inherent in the source code, be it relatively low-level stuff like the basic program flow, or relatively high-level stuff like control structures. The other explanation would be that this encoding of instruction still has that information somewhere but hides it. Both of those are true in part. Use some of the structure because, as said, what a compiler basically does, it converts all kinds of loops into ifs and gotos, because that's what processes actually execute. And that kind of structure is lost. But a lot of the structure really gets transferred in an easy way to the assembly code. And so we try to make this way the instruction encoding hides the structure of the code and what are individual commands and stuff like that. We try to reverse that so we can get better compression. There'll be some assembly code in this section, Intel assembly code. If you can't read that, just ignore it. It's not that important to understand it. It's all color-coded, so you can see what's going on and see what I'm talking about. This code example, which is just a dump from one of the Werkzeug routines, just a disassembly listing, with the actual code bytes, which is what the processor actually gets to see and gets to execute, highlighted. Now, this is all in different colors, and I colored this differently because those byte values encode different parts of the instruction. Some of that is addressing modes and stuff like that. Some of it is operands, and as you see, it's basically a random mix of different data types. It's first a few bytes of opcodes, then it's an address, then another opcode, then it's some relative offset, and this kind of data always has a very different distribution, a very different meaning. And it's all munched together because, that's all the information the processor needs to execute, and it all needs it for this one instruction, so it's all in there in the sequence in which the processor needs it. This is obviously a good idea when you're trying to build a processor, but not a good idea if you're trying to compress it, because you want to separate data that has a different meaning, and put everything with a similar meaning together so you can exploit the structure better. And what I color-coded here is different types of the opcode encoding for Intel instruction. Like here, you have instructions with some parameters, some addressing modes, and this gets translated into that string here. And the red one is an offset and stuff like that. So you can see here what gets mapped to where, and you really see it's kind of weird. It's very mixed. And it's not that it's systematic. It doesn't look very systematic. The reason for that is that the original instruction set was for a 16-bit processor, had far less instructions, and was based on completely different concepts. They always added and extended that architecture and basically added a lot of hacks too, and it's all very patched up by now because, it's a 20-year-old architecture, at least the original idea, and they always did some changes and some modifications, and by now it's basically a mess. You always have those different types of data in one big data stream, which are, for example, actual instruction opcodes, like the black ones here, or address displacements, like here, those red ones, or addresses themselves in the code and in the data and stuff like that. It's all mumbled together. And those values have